Hi, my name is Soha Hussein. Today I'll be presenting with Vaibhav Sharma our work on Java Ranger, statically summarizing regions for efficient symbolic execution of Java. This is a collaborative work with Mike Whalen, McCamant, and Willem Visser. Today I'll be talking about the motivation of this work, and then I'll give an overview of Java Ranger and its transformation. I'll then talk about the evaluation, and we will present our conclusion and future work. Now, symbolic execution is a program analysis technique that's being used for bug detection, test case generation, and equivalency checking. It has a known limitation of path explosion when it's trying to analyze large programs. One way to avoid exploring all paths is to try to merge them, and this is what veritesting does. Veritesting tries to path merge a program by summarizing their behavior into a disjunctive constraint. Now, this is all good and useful, but can we do similar thing for Java programs? Well, consider this piece of code. This code is trying to count the number of words in the list object where words are separated by 0. This code has an expansive if statement. The reason that this if statement is expansive is that it resides inside this while loop, and therefore symbolic execution needs to fork on it every time or in every iteration, really. So if we have a 200 objects in the array, then symbolic execution would require to explore 2 to the power of 200 execution paths to finish exploration of that program. Ideally, what we would like to have is we would like to path merge this if statement into a single exploration. In order to do that, we really need to summarize everything inside this if statement. That includes the call to the list.get. Now, this list.get has the control flow on the right figure. So ideally, what one would like to summarize all method invocation, and that includes resolving dynamics dispatch, dispatching the type of the list to an object of an array list, dealing with exceptions. That's another thing as well, which is caused by accessing an element that's out of bound. And we need also to summarize heap side effects to make the side effect of updating the array. And thus we present Java Ranger that does all of that. It's a path merging tool for Java programs. Java Ranger handles dynamic dispatch by allowing method inlining. It presents single path cases as a way of dealing with exceptions. And finally, Java Ranger supports internal creation of single-gated assignments for references to account for heap manipulation. And therefore, in fact, using this, Java Ranger is able to transform the 2 to the power of 200 execution paths in this program to a single execution path. Java Ranger has a series of transformations that takes in a region of code and applies these transformations until it obtains a logical constraint. Every transformation is designed to be simple and to deal with a concrete Java language feature. Java Ranger starts by intercepting conditional symbolic branches and creates a Java Ranger intermediate representation for the corresponding fragment of code that's trying to path merge right now. A region can either be a multipath region, which represents an if statement in the source code, or a method region, which represents a method in the source code. For example, this source code is mapped to this on the right Java Ranger intermediate representation, and this is really an example of a multi-path region. Next, Java Ranger tries to do alpha renaming of variables by giving variables unique names, and really the purpose of that is to maintain unique names for variables inside the produced summary, so that if we encounter the same region again, Java Ranger is able to produce different summaries. For example, using this IR, Java Ranger's IR on the left-hand side, gets transformed after alpha renaming by renaming all variables with unique prefix. In this example, it's _1. Next, Java Ranger performs an early return elimination transformation. And the goal really is to try to collapse all return paths into a single path that can explore all return possibilities. Then Java Ranger runs substitution transformation, and in this transformation, Java Ranger collects all runtime information from the symbolic execution environment and substitute them into the Java Ranger's IR statement. For example, this statement on the left is transformed after substitution to the statement on the right hand side, where all the blue variables are substituted by their runtime values. For example, x9 is transformed into 375, which is the reference number. Next, Java Ranger tries to inline methods. If the region that's trying to path merge right now has a method call, then it tries to find the type information from the environment and then inline the appropriate method provided the type. For recursive methods, Java Ranger inlines up to some user-defined depth. For example, the list.get is an invocation, and therefore Java Ranger grabs in the summary for the method.get and inline it in the appropriate way. Next, Java Ranger runs references gated single assignment transformation, and really this transformation looks for any reference, update, or lookup, and that includes fields or array updates and lookups. And it tries to capture the semantics of this computation by creating new variables that reflect the computation. For example, for this array update, Java Ranger reflects that as a series of a computation by creating new single-gated assignments and that reflect the update on the array. Next, Java Ranger applies single path cases transformation. And really the idea of this transformation is that Java Ranger allows path merging of partial regions where unsummarized behavior is explored independently using symbolic execution. For instance, Java Ranger does not summarize exceptions, and it does not summarize object creation, and therefore if the region of code that we're trying to summarize contains any of that, then Java Ranger collects the predicate that can guide symbolic execution to explore separately these unsummarized behavior. For example, this piece of code that Java Ranger is trying to summarize, there is an array access that can lead to an array out-of-bound exception. And since Java Ranger does not summarize exception, it will create a predicate that contains the conditions under which this exception can happen, and then guide the symbolic execution to explore that in a separate execution path. Next, Java Ranger runs simplification transformation, and really the idea here is that we're trying to simplify the constraint that we're going to put on the path condition. And Java Ranger does that by applying constant propagation and copy propagation and constant folding onto the summary that has collected so far. Next, Java Ranger runs linearization transformation, and in this transformation, Java Ranger tries to linearize the summary by removing all branching. And this is done by replacing if statement with a composition of its then and else statements. And this is correct as long as these conditions inside the if statements are captured, and Java Ranger captured them into the gamma expression. Finally, Java Ranger is now ready to create a constraint to be pushed on the path condition, and this is done through this transformation. So, for example, using the linearized summary, Java Ranger transform it using this transformation into a constraint that now can be pushed into the path condition. Now I leave the talk to my colleague Vaibhav Sharma, who will continue the rest of the presentation.
Thank you, Soha, for introducing Java Ranger and also for explaining all of its different transformations. Let's dive into its implementation. Java Ranger is implemented as a extension of an existing symbolic execution tool called Symbolic Pathfinder, or SPF. And the way Java Ranger works is that it uses a feature of SPF called listener. A listener is a piece of code that is executed before or after every single Java bytecode instruction. And so Java Ranger's listener essentially checks first if the instruction that is about to be executed, is it a branching instruction or not? And if it is, then Java Ranger checks if it already has a summary for the region of code which is about to be executed at the branching instruction. And if Java Ranger does have a summary, it then chooses to use the summary and then move SPF's current point of symbolic exploration to the end of that region of code. Now, not all path merging is beneficial, and so Java Ranger has a naive algorithm which checks to see if the number of single path cases being explored to the region of code by using the summary is strictly less than the number of execution paths which would have been explored through that same region of code without path merging. And so this extremely naive algorithm helps Java Ranger improve or not use path merging in certain cases. And finally, Java Ranger uses the incremental solving mode because we found that incremental solving actually was helpful in making Java Ranger's performance better as compared to the path solving mode of SMT solvers. Now we implemented Java Ranger, and obviously we want to check if it actually improves performance. And we came up with a bunch of different research questions for answering this. The first research question was, does Java Ranger actually reduce the number of execution paths and the total running time when it explores all feasible paths through a program? To answer this question, we came up with we actually found 9 different benchmarks. These 9 benchmarks have quite a diversity in terms of number of lines of code and also number of classes and methods. And this diversity is something that was important to us because we wanted to get an accurate picture of Java Ranger's performance, hopefully representing real world Java code. So the very first comparison that it made most sense to do was with SPF itself because Java Ranger extends SPF. And so we went about doing this comparison by letting each benchmark be symbolically executed with both Java Ranger and SPF within a 12-hour time limit, with the most number of symbolic inputs that would actually allow symbolic exploration of that benchmark to completely be finished for all feasible paths within the 12-hour time limit. So we did this comparison with SPF and Java Ranger and then found the following results. So first of all, for 6 of the 9 benchmarks, we found that Java Ranger did actually reduce the total running time significantly, and also it reduced the number of execution paths significantly. And for 4 of these 6 benchmarks, it used many thousands, and in one case, close to more than a million, actually, a number of summaries. So Java Ranger was clearly helpful for 6 of the 9 benchmarks. For one of the remaining 3 benchmarks, replace, it led to a significant reduction in the number of execution paths, but it actually led to an increase in the amount of total running time that was used when exploring with Java Ranger. And this was attributed to a large amount of solving time being spent when the summaries were used with the replace benchmark. Finally, with 2 of the 9 benchmarks, Java Ranger had no opportunity for creating a summary, which led to no change in performance between Java Ranger and SPF. We have 2 other research questions that are answered in the paper, but for the last research question, we also wanted to know how does Java Ranger do with respect to all the other state-of-the-art verifiers for Java bytecode. And so we entered Java Ranger into a competition, the Software Verification 2020 competition. And in this competition, Java Ranger outperformed all the other 5 participants in the Java verification track of the competition, earning the highest score and also the highest number of correct true answers. And also Java Ranger reported no incorrect answers, which led to its winning the Java verification track at SVCon 2020. Java Ranger's work is not done because when we have path merging, we still want to be able to produce test cases from the path merging symbol executor. Unfortunately, we want to be able to produce test cases without undoing all the benefits of path merging. And therefore, we want to explore in the future how to generate test cases with Java Ranger. We also want to be able to use path merging without affecting the ability of the symbol executor to be able to reach a certain goal quickly by using an exploration heuristic. And so we need to improve on the existing symbolic exploration heuristics, the guidance heuristics used for guiding a symbol executor to get to a goal quickly. And finally, too much of a good thing can also be bad for you. So if we have path merging with a symbol executor, if it path merges too often, Or actually, if a path merges too aggressively, as we saw with the replace benchmark, it can be bad for the overall running time of the path merging symbolic executor. And therefore, in the future, we want to explore if we can come up with strategies so that path merging is only used in Java Ranger when it is beneficial for the total symbolic exploration. In summary, Java Ranger extends path merging for Java symbolic execution. It does this by means of using all these different transformations where each transformation is really simple, but this means that all the transformations are independent of each other and allows for easy extension of Java Ranger with new transformations. Java Ranger is more or less only useful when we have long running verifications. If we have a short running verification, we are not going to see much benefit from the path merging symbolic executor like Java Ranger. And finally, even though Java Ranger does have path merging capabilities, it also remains a tool in this larger toolbox, which is the symbolic execution technique itself, wherein we want to be able to extend and apply symbolic execution with all these other strategies and benefits, such as exploration heuristics and generating test cases. And so this is something we are working on to improve Java Ranger in the future. That's everything. Thank you for listening to this talk. This talk was done in collaboration and the whole work itself with Soha Hussein, Mike Whalen, Stephen McCamant, and Professor Willem Visser. Thank you for listening, and we hope you get a chance to try out Java Ranger soon. Thanks.